Alright, so we were on this Bluetooth slide. So we will begin with details. First of all, it works in the same range as 11. So 2.402 to 2.480. This is exactly the band that 802.11 uses, and the total of 79 megahertz band. So while 802.11 uses only 20 megahertz channels, right? This one uses the whole band and frequency hops. So, so if it frequency hops, there are 79 frequencies at 1 megahertz apart. In some countries, there are only 23 megahertz available, so it will frequency hop in those 23 megahertz. Okay, and it gets you 1 megabit nominal, and the net is 720. So what happens is, when you hear the rates such as 11 megabits or 54.4 megabit, these are bit rates at rate which the bits are sent. But you know, there is a wait, there is a gap, and so on and so forth. There is a collision, and so the effective rate generally is much less than the what we call the nominal rate. So this is basically tells you the size of the bit is 1 megabit per second, right? But by the time you take care of other overheads, you get more like 720 kilobits per second for the user. Channel bandwidth is 1 megahertz. Up to 10 meters can be extended. So basically it goes up to 10 meters, and you can go longer by higher power. With a normal power, it is 10 meters. Why does it keep going up? As I said, it is frequency hopping 1600 times per second. So it remains at one frequency for 625 microseconds. It means at one frequency and then hops to the next frequency and then hops to the next frequency. So you remember frequency hopping, right? The spread spectrum technique, right? There were two spread spectrum techniques. One was frequency hopping, another one was direct sequence. So this one uses frequency hopping. And it has a 128-bit encryption and challenge response authentication. So what is challenge response authentication? So normal authentication is a password. We say, what is your password? You give the password, and then we verify that's the right password. But the problem with that is that I mean, anybody can probably replay it, or or can probably listen to your password unless it is also encrypted. So there are ways to get rid of that problem, and one simple way is to do challenge response, where we send you a challenge. We say, okay, all right, whatever your password is, with that, please encrypt this number. And then you use your password to encrypt the number. When the number comes back to me, I can do the same thing, and I have your password, so then we can verify that, yeah, your password is correct. So that is called challenge response. No password is exchanged. A random challenge is sent to you, and then you have to send a response to that random challenge. And that way you cannot replay it. Does it make sense? Does it make sense what is challenge response? Why it cannot be replayed? Because the challenge is every time different. Right? So even their password has not changed, because the challenge is different, the response will come out different. Alright, and then power wise, there are three classes, class 1, 2 and 3. Class 3 has the lowest power, which is 0 dBm. How much is 0 dBm? How many watts is it? Anybody knows how many watts is 0 dBm? 1 milliwatt. And a higher power is 4 dBm, class 2, and 20 dBm is class 1. And they can go longer just because they have more power. you should read, well, you can read one of these 3 pages referred here for more details, but today I have added actually the Wikipedia page too, and that is very good actually, I found. So I mean, at the end of this handout I put Wikipedia page, but you can probably write down in your handout that you should read that at least for the exam and other things. Alex, how does this work more? And basically, one device acts as a master, and other devices act as slaves. Okay, so it turns out that this shows you the age of the standard. We no longer use the word slave anymore in any networking protocols. We call them primary and secondary. So the new terminology would be, we have one primary station. Our master station is fine, but then we will have secondary stations. Anyway, so there are 7 slaves here, and the reason one master is because that acts like a base station. So it basically coordinates the whole thing. Generally, in most communication that you are using Bluetooth, there are only 2 stations. I mean, you are talking to one cell phone to another cell phone, or from one cell phone to your computer. So whoever is more powerful generally becomes the master, and the other one becomes the slave, and the master controls everything. So anyway, so up to 7 active slaves. So for example, if you have one computer which has a Bluetooth in it, it could be talking to 7 devices. It could be talking to a printer, it could be talking to your phone, it could be talking to some other device, right? So that's what it is. 7 active slaves and 255 parked slaves. Up to 255. So the total is actually 256 only. So basically 255 is total actually. So basically what it is that you can have up to 255 nodes in a network, in a Piconet as we call it, and all of them could be parked, or some of them could be active. Up to 7 can be active. So parked means they are sleeping, right? And so they are not really losing any battery power that way. Active slaves are polled by the master for transmission. So 7 slaves which are active, they are continuously polled. Do you have anything to send? 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 And if you have something to send, you say yes, and then we give you opportunity. I mean, the master gives you opportunity to speak. Right? That's why it is called the master, because a slave cannot just speak by itself. It has to wait until the master asks, do you want to speak? And you say yes, and then you speak. All right. Each station gets an 8-bit parked address, and that's why the limit is number of parked addresses, because the address is 8-bit. And so when you join the network, you get an 8-bit number, and you say, well, you are number 15, you are number 233, and so on and so forth. So you get an 8-bit address, and then if you are parked, means you are sleeping, you can come back in 2 milliseconds. Whereas if you are just coming in fresh into the room, it will take longer than 2 milliseconds. So when you come, you join the Piconet and go to sleep. And then if you want to speak because you have a traffic, then you come back to active stations. A device can participate in multiple Piconets, and that is a complex schedule. So while this is more like, this feature is more like a theoretical feature where one device could be talking to 2 different masters. So it is there, but I haven't seen it happening in practice. All right. So in practice, we generally have 2 devices at most, maybe 7, maybe that would be already too much. But this is how it works. All right. So everything on this slide is clear before we move on to the next slide. Any question about this slide? Any feature? Okay, go ahead.
Just very quickly, is the total 255 or 256?
Okay, so actually, if you don't count the master, then 255 plus 1. Master is plus 1.
Okay, thanks.
because you need 8-bit addresses. So if all 0 address would be the master, right? And then you have 255 others. So that is the total. And if some are active, some are parked, all of them could be parked. All right, let's already move to the next slide. All right. So the next slide talks about how does the frequency hopping work. So we already have done this frequency hopping thing, but we will see an exact implementation in Bluetooth. So the way frequency hopping works is that there are many frequencies to which we randomly switch. Every 625 microsecond, the frequency is switched using a pseudo random number generator, right? So with a pseudo random generator, if you have the formula and I have the formula and we can put a seed into that formula, same seed, we will get the same number. You put the same number again, you get the same number again and again. So we will get exactly the same sequence, even though it is random sequence. But if we start with the same formula for generator and we start the same seed, we will get the same number, right? So both of us or all of us will know exactly what frequency we are working in this slot. Alright, so we go from frequency to frequency to frequency. Every 625 microsecond we change the frequency. Well, not okay, we don't change the frequency every 625. The slots are 625 microsecond, so we could potentially change the frequency every 625 microsecond, but if we start a transmission and if it is multiple slots, then we continue on that frequency. That's the thing. So it uses time division duplexing. Now I think we discussed FDD and TDD. Anybody remembers what is TDD? How do you do duplexing? What is duplexing in the first place? Bidirectional communication. And what are the two different ways to do bidirectional communication? FDD, one is frequency, one is time, right? TDD is time. So in time basically means half duplex, in some sense, right? You speak half the time, or not half the times. When I am speaking, you're not speaking. When you are speaking, I am not speaking, like that, right? So this is the TDD. Downstream and upstream alternate. Master starts in the even numbered slots only. So the slots are numbered. So if you have 0, 1, 2 and so on and so forth, so the master will speak only in the even numbered slots. Slave start in the odd numbered slots only, and LSB of the clock indicates even or odd. So there is a clock, and whenever the least significant bit is 0, that means it is even. When it is 1, it is odd, right? Slaves can transmit one slide right after receiving a packet from the master. So here is a master speaking, and this is the slave speaking. So you see, the slave can speak right in the next slot. So actually this is just the next slot, not one slot gap, just next slot. Then packets are either 1 slot long, 3 slot long, or 5 slot long. So the packets could be, this is 1 slot packet, this is 3 slot packet, and this is 5 slot packet. Shown here, okay. The frequency hop is skipped during a packet. So we change the frequency every 625 microsecond unless you are transmitting a packet. So in the middle of the transmission, you don't change. So if you are transmitting here, basically the master is receiving. In that case, both of you don't change the frequency, right? But once the transmission is over, we change the frequency. Because if you change the frequency in the middle of the transmission, you will lose some time, and that's not very good, right? So we don't change it during the transmission. Otherwise, we change every slot. Okay. So frequency hopping of Bluetooth, is it Clear now? Any question about this? David? H? Okay. Are you following? Did you miss last class? Okay, alright, so you might be a little behind. Please catch up on that one. Okay. Alright, if there are no questions, then we move on to the packet format. So the packets can be up to 5 slots long. 5 slots will mean about 3125 bits. 3125, you can calculate how many bytes that is. Anyway, so the first 72 bits are access code, the next 54 bit is the header, and then the payload is the rest. The access code identifies the Piconet. So there could be many Piconets going on at the same time, and the reason they don't interfere is why the different Piconets going on. So you are transmitting, talking to some other, two cell phones are talking here, and the other two cell phones are talking just next to each other. Why there is no collision? Anybody can think about the reason how it works? Why? I mean they can do it in parallel, multiple communications. What is the access method here? Yeah, they're all hopping on different frequencies. So even though they are using the same band, these two people might be hopping at some frequencies while the other people are hopping at other frequencies. So they all know their frequencies and their Piconet and so on and so forth, right? So that's what is happening is, so multiple, but when you transmit, you announce that, okay, I'm talking for this Piconet, and so, there's no confusion. Just in case there is somebody else who happens to come to the same frequency at that time, but on a different Piconet. Alright? To avoid that collision, you put that, so either, two things will happen. Either you will just hear a garbled thing because two people are transmitting on the same frequency at the same time, or you may hear one of them, in which case you will know that's the wrong Piconet. Right? If it is wrong Piconet. Alright, so that is the access code. Channel access code identifies the Piconet. Device access code for paging request and response. So the access code has many parts of it. And then the inquiry access code to discover the units. So basically in the access code you have the identification for the channel, which is SSID kind of thing. And then you have identification for the device. Okay, so we will see its use when we see the paging and other things, and the inquiry mode. Inquiry mode is used to discover the units, to find out if there is somebody else is speaking Bluetooth here. So the header itself, which is 54-bit, has 3 bits of member address. Alright. So what happens is, while everybody has bigger address, the address itself is, complete address is not used. 8-bit address is assigned when you join the Piconet, and 3-bit is the number for the active nodes. So when you are active number 1, active number 2, active number 7. Right? So that is the member address. Type code is the 4-bit, what kind of packet it is. Flow control, ACK or NAC is 1 bit. Sequence number and the header checksum 8 bits. Header is encoded using 1/3 rate FEC, resulting in 54 bits. Okay, so instead of 8 bits, sorry, the total is 18 bits, and it becomes 18 times 3, 54 bit, because it is transmitted 3 times. Okay, that is the 1/3 rate mean. Is that basically you need to do 3 times as many bits as that. Alright, so let's see. And synchronous traffic has periodic reserved slots. So one thing I haven't talked about is synchronous traffic. So So there are two kinds of traffic on the Bluetooth. One is the voice traffic. It was originally designed for telephones, so it has a special channel for voice. And the voice doesn't have packets and things like that. It is just reserved bits. So it's continuously, basically you send the bits. So that is synchronous traffic. And so synchronous traffic has periodic reserved slots. So there are reserved slots, and you don't have this all this header and all that. You just every bit there is voice bit. And other slots can be allocated for asynchronous traffic. So everything else, when you're sending files and other digital bits, then they go through the asynchronous traffic. Okay. So the voice is handled separately, and that is called synchronous. It has reserved slots, which are allocated depending upon what speed voice you are using. And other than that, everything else has to use this method where the master will poll you and ask you whether you want to transmit, and if you want to transmit, then it will allocate you, ask you to transmit. So a station itself can be in one of these states. So any station which is not connected is in the standby, and that is what most of the phones are, in the standby mode. And actually when your Bluetooth in your computer is on, it is in the standby mode. And that can take some battery, by the way. So if your battery is weak, one of the things you can do is turn off the Bluetooth. Alright? And that way you will save some battery, because even though it is not talking to anybody, but it is continuously asking, is there anybody who is speaking Bluetooth? Right? And so that is the standby. From the standby mode, it comes to inquiry and page. So page mode is basically, and so this is the standby is the inquiry mode is the master sends the inquiry packet, and the slaves scan for the inquiries and respond with their address. So basically, master says, does anybody want to join? And so you look for that message, and if you want to join, then you say yes. And the master in the page state invites the devices to join the Piconet, and the page message is sent in 3 consecutive slots on 3 different frequencies. Slots, and the slaves enter the page response state and send the page response including the device access code. Alright, so now once the inquiry is sent, then the master says, okay, I am going into the page state, anybody who wants to join, please send me, now it is time for you to respond. So please send me your basically authentication and things like that, so access code. So you send your access code. So you say, well, I am the cell phone and I want to talk to you, and my access code is such and such. So the access code is generally, we all program it to 0000. So it doesn't really work that much well, but you are allowed to program it to anything else, right? So once you program that access code, both devices, if they know the same access code, then they can talk to each other. So you use, so basically, inquiry mode is what we would call the beacon mode, and the page mode is what we would call the joining mode or login mode. And then the master says, all right, here is my clock, here is my address, and so the slaves can participate in the Piconet. So basically, now they have the number, exactly the clock number that people are counting, so you know which is even, which is odd, and all that comes in that information, and then you become connected. Once you get connected, then you get a 3-bit logical address. So that is, you are active, and you get the 3-bit logical address, then you can transmit whenever you are allowed to transmit. So let's go back to this diagram here. Standby mode is when you are not talking, then you hear an inquiry, then when the master goes into the page mode, you get connected, and once you get connected, you can transmit, and then you can go back to standby if you need to, or you can remain active right here. When you are connected, you can also go into one of these 3 modes. which is you could go into park mode, you could go into sniff mode, you can go into hold mode. So these are three sleeping modes. All three are sleeping modes, and there are three different levels of sleeping. Alright, we're going to talk about that in a minute. But any question about this diagram before I move on to the sleeping modes? You have a question? Do you guys have a question? You were talking. Do you have a question about this or previous or next? Makes sense? Okay. Alright. So basically, key thing in this slide is this, that this is sent by, inquiry is sent by the master to say that, well, I am available here, anybody wants to join. And then it goes into the page mode for the next 3 slots. So anybody can join. And when they join means they tell that this is me and I want to join, and then they get connected, and then the normal polling operation will take place between this, and you stay in this mode for most of the time. And when you want to go back to sleep, you just go into this mode. Alright, so sleeping mode. There are 3 sleeping modes. And so the hold mode is, in this mode, you don't have any data traffic going, but your voice traffic continues. Alright, so this is hold mode where the data mode is on the hold, so we don't poll you and you don't waste your energy in polling. But if you are talking, that continues, and then since that is a reserved slot, in the data slots you can do anything else you want to do, which means that you could join another network, you could scan the network, you could if you are a master, you could go into page mode or inquire. The sniff mode is a low power mode where you just go to sleep. So this is low power mode where you are kind of half awake, half asleep, and you wake up after fixed sniff intervals. So you wake up every few slots. Well, park mode is very low power mode. You give up your 3-bit active number, and then you get an 8-bit park number, and you just go back to sleep. Okay. Packets for parked stations are broadcast to a 3-bit 0 address. So this is what 0 address is used for broadcast. And so when there is something for somebody, they have an 8-bit address, so that 8-bit address will be announced in the broadcast that I have a packet for node number 15. So whenever node number 15 wakes up, they will hear that broadcast, and then they will change their state from park to active. Right? And that will take 2 milliseconds, as we said before. Why 2 milliseconds? Because there is a cycle over which all this is allowed. So normally the transmission is going on every few milliseconds, then there is an opportunity for you to join. So anyway, so there are 2 states. This sniff state is actually kind of active state because you still keep your 3-bit address. So you don't lose your 3-bit address, but you are sort of sleeping, whereas this is you are fully sleeping. Okay. You can imagine that when is the sniff state is going to be used. If you are going to be active more than 2 milliseconds, once in 2 milliseconds, then you might as well not go to sleep because it takes 2 milliseconds to wake up, right? So you want to go into this half sleep state. And some of the really low rate devices such as GPS, generally many of the GPS devices, well, alright, this is the thing, many of you have not seen those GPS. So when the GPS first came out, the satellite receiver was separate than the GPS device. I don't know if any of you have seen those 2 things. There were 2 pieces, satellite receiver, and either your cell phone could act as a GPS device, in which the GPS is not built into your cell phone, but you could connect to a GPS device externally, and they used Bluetooth. In that case, the rate is so low, even though it is continuously active, you are looking at your map continuously, and the device is giving you the data, but it is in terms of could be once every 10th of a second, right? And so that could go into the sniff mode. The GPS could go into sniff mode, or the cell phone would go into just sniff mode. So that is the thing. And so right now, for example, my computer is not talking to any Bluetooth device, but the Bluetooth is on. So basically, all it is doing is coming up sometime and sending out an inquire message, figure out if something wants to talk to it, and if my cell phone wants to talk to it, then they are probably connected. I don't know. I mean, I haven't checked that, but you can check whether your cell phone is connected to your computer or not. But as long as they know each other, they have the code, they could be connected and then go back to sleep in the park mode. Okay? Any question about parking? Yeah?
So, the last bullet point, if somebody has a packet to send to a park station and they broadcast it through the address,
Okay. Right.
park station address.
So everybody, when they want to talk to everybody talks to the master, right? The slaves don't talk to each other, right? So if you have a packet which is addressed to somebody who is parked, you will send it to the master, and in the packet there is a destination address of some kind, which could be 8-bit or 3-bit if it is active, right? And then the master will keep it until the park really wakes up. Okay?
So, I mean, in a Piconet, there's never going to be more than one device that's going to be accepting broadcast packets. So why is there even a zero?
Okay. The reception is broadcast and everybody is listening to the broadcast. What do you mean by only one device is listening?
Well, I mean, isn't all broadcast traffic destined for the master manager?
No, hold on. The master broadcasts to all the slaves, right? That's the broadcast.
I don't think I follow. I mean, I'm not really sure why would the master know to be sending a broadcast to some park station?
Okay, so this is like beacon actually. The thing is, we haven't discussed the details of the inquiry message and things like that, but say for example, inquiry message is actually a broadcast message, right? It is not addressed to a particular node, right? But there could be other messages which are required to run the network, which which are sent, which could be broadcast, which are addressed to everybody who is on the network, right? So broadcast is generally used for network control rather than any data transfer. Control and management, let me put it this way. If you want to distinguish between those. Okay? And as seen here, actually the slaves have nothing to broadcast actually. So the thing is, it's the master which wants to control the network, and it has all the information that it wants to tell everybody. So rather than telling 7 people 7 times that my clock is so much, my clock is so much, my clock is so much, it might as well just tell in one broadcast message. Okay? Is that clear? Anybody else has any question? All right, so the power is one of the key considerations in the wireless network, and one way to measure the power consumption is how many watts or how many joules of power energy is used for 1 megabit, for 1 megabyte. Alright. So in 802.11b, the bit rate is 11 megabits. The power is 50 milliwatt. If you were to convert that into joules and then divide by the bit rate, you will get 36.4 millijoules per megabyte. Now here are a few things that you should remember. Every time when we use a little m, that is, little m is milli and capital M is mega. Okay. Little b is bit, capital B is byte. Okay. Now let me ask you this. Anybody knows what is little k and capital K? Yeah. Capital K is 1024 and little k is 1000. That's the confusing one. Many people don't know that. Alright, having done that, now let's see. 802.11b has 36.4, 11g has 7.4, 11a has 29.6, and this is Bluetooth, is 8. And this is, we haven't talked about it, and Zigbee is 0.03. So basically, as we are going in time, you can see, notice the time. This is the oldest standard, this is the next one. These two are both oldest actually at the same time, A and B. Right? They require a lot more energy than the newer ones, which are Bluetooth and G. And Zigbee is even lower. So Zigbee devices can have batteries that can last for years. Okay? Whereas Bluetooth devices have to be basically charged every day. Alright? And so the magic is not in the battery, but it is in the protocol. Now Bluetooth stack, protocol stack is slightly different than what we normally see in the IP world. Or the ISO OSI model, whatever is there, but here is the protocol stack. So there is these are the layers which we are going to describe in the next few slides. But one thing to be clear in this slide is that there is this audio track here, right here, audio. So the voice goes straight from physical layer. These two are both physical layer, by the way. So it's straight from the physical layer to the application layer. So there is no packetization, nothing, it's just the bits. As the voice comes in the bits from, let's say you have a headphone talking to your cell phone, the bits are being transmitted by the cell phone, they come into the headphone and they go straight into the application to be played. So there is only thing is required is a connection. So before that connection is set up, once the connection is set up, you need a synchronous connection to be set up. Once the connection is set up, then the bits just go straight. The rest of the traffic goes through all these protocol stuff, and let's just describe that one by one. Now RF and baseband, these two are the frequency, these two are the physical layers. This is simply the frequency hopping layer. So this is basically, we talked about the frequency hopping, but then we also use what we call GFSK modulation. Gaussian frequency shift keying. Now basically the key is that this is a frequency shift keying. Frequency shift keying means that we use one frequency for 0, another frequency for 1. So if you want to send 101010, we will send whatever frequency for 1 bit time, change the frequency for another bit time, and so on and so forth. Gaussian is basically a filtering after that. So once you do that, it turns out that the spectrum doesn't really look very good if you just continuously change frequency like that, and therefore then they do Gaussian filtering of that spectrum, and we don't have to go into that detail, and that is the detail that physical layer people worry about. So this is the modulation which is very common. In fact, if you have a GSM phone, which is like AT&T phone, GFSK is used in GSM also, right? So it's a commonly used modulation technique. Baseband is the connection and the media access control. So there is more detail of the baseband layer. So each device has a 48-bit IEEE MAC address, which is divided into 3 parts. This is 48-bit. The lower 24-bit is called the lower address. Middle 16 bits is called non-significant address, and 8-bit is called upper address. Now, those of you who took 473 might remember how the 48-bit addresses are assigned. They are assigned by IEEE. First 22 bits are actually first 24 bits are what we call, okay, the first 2 bits are universal and group bits. One says there is universal or non-universal. Second says there is a group or non-group. Anybody remembers what is a group bit mean? What is a group? Anybody remembers multicast or unicast? Alright, anyway. Now you guys who took this last semester 473, you cannot forget so fast. There are at least 2 or 3 people here who took the 473 just last semester. Some of you probably took it much earlier and forget as to how the 48-bit addresses look like. But anyway, so when you have a 48-bit IEEE address, the first 2 bits indicate whether this is a multicast. First bit indicates whether it is a multicast or not. Second bit indicates whether it is a universal or global, universal or local. And then the 22-bit indicate who made that device. That is the organization that made that chip for the Ethernet or whatever device is using the address. And then 24-bit are the device. So if you have a company that makes anything to do with the IEEE addresses, you have to go to IEEE, pay $1,000. They give you 24 bits, first 24 bits. Then you can just start producing devices with numbers 1, 2, 3, 4, 5, 6, 7. So those go in the last 24 bits. Alright? So that is the most important part. That is what is used here in Bluetooth. And this is the part which simply tells me who made the device, right? Alright, so the address is divided into 3 parts, and then this 16 plus 24 bit, this is the organizationally unique identifier. This is OUI. And then the LAP is used, which is the lower address part, is used in identifying the Piconet and other operations. So if the master looks at this address, and whatever is the 24 bit it has in the lower part, that is what is used to identify the Piconet. Rather than calling SSID like we have in 11, this is the ID. The ID is the lower 24 bit of the master's address. Alright? And the clock runs at 3200 cycles per second or 325 microsecond, and that is twice the hop rate. Basically hop rate is 625 microsecond. So every 2 bits as the clock runs, every 2 cycles of the clock your slot is over. So the cycle is 1/2 of a slot. Slot time is 625 microsecond and the cycle time is 12 microsecond. Okay, half the so the clock is running at twice the rate of the hopping rate. All right, so that is the baseband layer. The baseband layer, we finished. Now we are going to go do the rest of the layers. So then we have L2 cap, which is the logical link control and adaptation protocol. So this does protocol multiplexing, segmentation and reassembly, and so let's discuss these two before we go to the third line. So protocol multiplexing means that if there are multiple protocols that are being used in the higher layers, in this case there are 3 protocols being used: TCS, RFCOM, SDP. So this one does the multiplexing. So there is some bit in this part of the header which indicates that this has to go to TCS, this has to go to RFCOM, this has to go to SDP, and when the packets come in, those bits are put in so that when it goes to the other side, they can give it to the right protocol. Right? That is protocol multiplexing. Segmentation and reassembly, which is kind of obvious that the packets coming from the higher layer might be bigger, they have to be segmented, and when they go to the other end, they have to be reassembled and given the same packet size. So that is the part of that L2 cap. Controls the peak bandwidth, latency and delay variation. So it decides which packet goes next, and therefore it can affect the delay variation and how much bandwidth who gets it, right? Then there is host controller interface, SCI, host controller interface, which is this part. And then there is RFCOM layer, which is the RF communication. So this is basically a layer which provides a serial port. Okay. So let me explain what is serial port. So before, if you remember, in the old computers there are serial ports, right? 15-bit ports. They look like a VGA but not a VGA port, right? 9, I think there were 9 pins, maybe not 15 pins. Those are serial ports, and many devices in the beginning used serial protocol. There was a protocol set up to do serial communication, and serial means that you just send 1 bit at a time. So you want to send 1500 byte, you just send 1 bit at a time on the wire. That is serial. So many of the original devices, the devices that we want to use, like printers, printers are parallel ports because printers are much higher speed. But most of the low speed devices in old days were serial. So when Bluetooth came about, they wanted to replace the serial port with the Bluetooth port. So they provide a simulation, or emulation, let me call it this way. They provide an emulation by the RFCOM. RFCOM simply emulates a serial port. So any application which talks to the serial port can talk to RFCOM, and then it will go over the Bluetooth. At the other end, it will come out again to the serial port. So how many people have seen a serial port? So rest of you have not seen a serial port ever? So you have to find an old computer and you will find a serial port there. Nowadays they don't make any more serial port because we have Bluetooth, right? But some of the old computers you might find. Alright, then alright, let's move on to the, so this is clear. What is RFCOM? It provides a virtual serial port. Then there is service discovery protocol, and each device has one SDP which acts as a server and a client for service discovery messages. So each device provides a service. So when you have a headphone, it's providing a service. What is the service it's providing? It's providing a headphone service. When you have a telephone, it's providing telephone service. When you have a computer, it is providing some kind of service, and printer is providing printing services. So all these services are basically announced by that device. The printer says, I am a printer, sir, I provide print service. So that goes to this SDP port. So each device acts as a server and a client for a service discovery message. So if somebody is looking for a printer, they will send a message through master, a broadcast message about I need a printer, and then the printer will say, here I am. I provide a printer service. IRDA is the infrared. So okay, so that basically, so this is another message here. IRDA is Where is the IRDA interoperability protocols? TCS. That's the only thing which is left here. So I assume that is the TCS. No, TCS is telephonic communication. IROBEX. Okay. We have to figure out what happened to that. Alright, anyway, so another interoperability that is provided by Bluetooth is the IRDA. So as I said, serial ports were very common, and then the next thing which was common for the low speed devices was the infrared. So the computer used to have infrared port, and then you can talk to another printer or another device using infrared. So Bluetooth provides an emulation for that as well. Right? And that emulation basically higher layer protocols don't need to change, only the physical layer changes to Bluetooth. And basically the physical layer of that application, whichever is using IRDA, will talk to Bluetooth. So there is this module called IRDA Object Exchange and IRDA Mobile Communication. Those are used for IRDA. Then the audio is carried over the SCO link. We talked about that. The audio goes on the synchronized link, and then the telephone communication specification binary. And then there is another protocol called TCS, which is used for telephone communications and things related to call forwarding, group calls, multiple extensions, and so on and so forth. So all that is part of the TCS. And on the top of these three layers is the application layer, and the application layer then implements headset, cordless telephone, intercom, LAN, fax, serial line, and so on and so forth. So there is a limited set of applications that can run on Bluetooth. It's not like TCP/IP where you can just write your own application and you can start talking. The Bluetooth devices have 13 or 15 applications, and each device has a particular application, and the application is standardized. So if you are a headset, you have to follow certain things, and so that any headset can talk to any other device that is looking for a headset. Right? If you are a phone, then you use that application, phone application, using the TCS layer, and then you come down, and so on and so forth. Alright? So let's just review it here. So there are many application profiles, maybe 13 or 14 profiles. That means there are 13 or 14 applications, and each application is standardized, and then they have a particular path to follow. The audio goes through this one, the telephony goes here. So now when the telephonic control goes here, basically, when TCS is telephonic control in that sense, right? So when you want to set up a telephone call, all that control will go through here. Once the call is set up, then all the audio will go through here. Okay. This is serial port emulator, this one is service discovery protocol. So this is how you figure out, if that service is available. So if you're looking for a GPS service, or if you're looking for a headphone or telephone or anything else. Okay. That ends the Bluetooth chapter. The summary is that it is good for 1 to 10 meters, very low speed, and the data rate is 720 kilobits at the user level. 1 megabit is the nominal rate. It uses frequency hopping, and it has application specific profiles, and that means that whatever application is done, then there is a whole set of basically standardized profiles which says that this is, if you are a headphone, you do this, if you are this, you do that. So those are the profiles. We didn't discuss each profile, but if you find a book on Bluetooth, which there are many books, then they will have chapters on each of these profiles. Okay. All right. So that brings us to the homework number 8. In the middle, actually, I have added this slide. You don't have this slide, but I have just added that, and it's very easy to find out. I didn't no need to print it. But basically, you go to Wikipedia and look for Bluetooth, find the link, and I found that the link had good information. All of this was there actually. Everything we discussed was there in that article. So that's a good place to read. And then there is a homework. Now here you think about this homework. This homework is not due. Why is it not due? Because next Monday is exam, and I know that you will read this chapter for the exam. Right? So I don't have to make you read it for the homework. Alright? So the homework you do on your own, and if you have a problem, you can ask me in the next class before the exam. But this would be just to make sure that you know this kind of stuff, because we might ask even, like any other homework, we can ask this homework as well in the exam. Alright? So don't be confused. Homework number 8 is not due. Alright? It's clear to everybody?
Is there a number 7?
Well, no. Actually, what we do is, there is no 7. We number everything by the lecture module. So this is module 8. That way we can add more homeworks in middle. Alright? Now let's just read the homework though. Assume that in one slot, Bluetooth, 256 bits of payload can be transmitted. So one slot is 256 bits. How many slots are needed if the payload size is so much? So what's the magic here? What is it that you are supposed to know?
The packets can be several slots long.
7 can be?
I said packets can be several slots long.
Yeah, how many slots long can they be? Yeah, right, that's the magic part. So if the answer comes out 4, you need how many slots? 5.